Well, you've done it. You finally made it to video number 7 in Unit 13, talking about acids and bases. And boy, howdy, have we saved the best for last. Okay, I'm not going to lie to you guys. We're going to be talking about a lot of math in this video. And so if your eyes glaze over and your brain starts turning into broccoli, don't feel bad. Because some of the math, it's a little bit tricky. Just write stuff down on your notes. We'll talk about it in class, okay? I promise you it's nowhere near as scary as it might look. Okay, remember, pH is a way of measuring how acidic a substance is. It is related to hydrogen concentration. Specifically, it's related to the negative logarithm of hydrogen concentration or hydronium concentration in a solution. Water, remember, naturally ionizes. Water molecules can just randomly split and become hydrogen and hydroxide ions, and so you end up with both hydronium and hydroxide in water. Now, somebody figured out a long time ago that those concentrations were equal, and the concentration of hydronium, or hydrogen ion, is 1 times 10 to the negative 7th moles per liter, and the hydroxide concentration is also 1 times 10 to the negative 7th moles per liter. So if you take this times this, then what you're going to end up with is what is called water's ionization constant, which is 1 times 10 to the negative 14th. Let me go back a slide. Look here. Anytime you multiply two numbers that have the same base exponent, basically all you have to do is add their exponents. So what's negative 7 plus negative 7? It's negative 14. Okay? So, now this doesn't just hold true for water. Here's the cool thing. For any acid or base, something dissolved in water, if you take its hydronium concentration and multiply it times its hydroxide concentration, you will always get 1 times 10 to the negative 14. Well, so what? Well, so everything, but wait till later and I'll show you how to use that. It's really, really super handy. So, if you've got a solution and you know its hydronium concentration, you can figure out its hydroxide concentration. All you have to do is take this divided by the one you have to get the one you don't know. It's really pretty easy. Now, because these numbers, these times 10 to the negative 7th and 8th and 9th and 11th and whatever, get so huge, using the pH scale is just an easier way of expressing that big concentration and making it smaller. So if I've got the hydronium concentration, the hydrogen concentration of my acid, I go to my calculator, I hit negative log, and put that number in, it'll spit out the pH. Okay? So for instance, if I've got something like water, 1 times 10 to the negative 7th, I hit negative log 1 times 10 to the negative 7th, and I hit enter, it's going to spit out a 7 at me, which tells me I've got a pH of 7. Now here's the cool thing. There's also something called pOH. Now we don't use it quite as often as we do pH, but pOH is pretty much exactly the same thing, except you're looking at the concentration of hydroxide instead of hydronium. You're looking at how strong of a base it is. Any solution, if you take its pH and you take its pOH, you can add them together and they will always add up to 14. The reason they'll always add up to 14 is the same reason that when you take this and multiply them, they always give you this to the negative 14. It all has to do with those decimal places and a logarithm. Okay? Now we're going to get to the very last little bit right here, talking about titration. This is how you can figure out how much hydronium or how much acid or what concentration of acid you have. For instance, in class we used some hydrochloric acid to take the zinc out of the inside of pennies, and if you remember, first time we did it, we didn't quite get all of the zinc out of the pennies because it used up all of the hydrogen ions that were in that acid. Well, if I know how much zinc is inside of a penny and I know exactly how much acid it takes to get it all out, then I can actually use one to figure out the other, and that didn't make any sense at all. So let's just stick with the definition here. If you use a known concentration and you react it with something that's of an unknown concentration, when it stops reacting, it'll tell you how much of the unknown stuff you had. Okay? I'm not entirely sure why this is, oh, I know why that's thrown in. So if I've got what I know right here, if I've got a known molar concentration and a known volume, however much volume it took to completely react, I can then know that that molarity times volume is equal to the other substance's molarity times its volume. So if I've got 500 milliliters of my unknown here, and it takes 250 milliliters of this, I can use that to figure out my unknown molarity. Very simple algebra. Of course, it gets into making sure you know how to balance those equations, so really hope you haven't forgotten that. I'm not sure how much of that stuff you've got to write down. I'll give you just a second to do so. Doody-doody-doo. You probably have this muted anyway. You can't hear anything. I'll tell you what, if you're still listening to me, the first 5 people who come to me and tell me what the secret password is, I will give you 10 extra points on your, let's say, lab average. How about that? Now, don't tell anybody. They got to find it in the video. The secret password is onomatopoeia. Okay, so let's take a look at an example here. We've got 27.4 milliliters of 0.0154 molar barium hydroxide. We put it in a 20 milliliter sample of hydrochloric acid, and we want to figure out what the molarity of the acid solution is. Well, you know that the volume times the concentration of the barium hydroxide is going to be equal to the volume times the concentration of your hydrochloric acid. So you take that times that, divided by that, and it gives you the concentration. Very simple. And guys, we are at the very end of the Unit 7 videos, so be sure you bring these to class when we take the test. Thanks again for watching. Tell your friends.